Now I'll take up the numerical example on the design of the gusseted base. So the problem is design a gusseted base for a column ISHP 350 at 710 Newton per meter with the two plates 450 mm by 20 mm carrying a factored load of 3600 kilonewton. The column is to be supported on the concrete pedestal to be built with M20 concrete. So the column I section column ISHP 350 at 710 Newton per meter. It is having two cover plates with the flange 450 mm by 20 mm. So we have to design gusseted base for this a column. So now the procedure solution of this design of the gusseted base. So design of a gusseted base. Design of the gusseted base. So now first step is the area of the base plate. So area of base plate equal to the factored load PU divided by 0.45 FCK. So PU is 3600 Newton divided by 0.45 FCK is 20. So this is the area of the base plate equal to, it is 4 into 10 power 5 millimeter square. Area of the base plate equal to 4 into 10 raised to 5 mm square. Now select ISA 150 by 115 by 15 mm gusset angle. Select ISA 150 by 115 by 115 by 15 mm gusset angle and 2 and 16 mm thick gusset plates. Okay, so the minimum width of gusset base equal to, minimum width of the gusset base is equal to 350, that is the column size. Depth of the column is 350 plus there are two cover plates, so 2 into 20 plus 2 gusset plates 16 mm thick plus the horizontal leg of the two, that is 115 ISA the angle section. Okay, so this is a minimum width of the gusset base required 652 millimeters. Now let us provide width of base plate. Width of base plate equal to 700 mm. Then the length of base plate. Length of the base plate equal to area, that is 4 into 10 raised to 5 divided by 700. So this is equal to 571 millimeters. Hence now provide a gusset base plate of size 700 mm by 600 mm. 700 mm by 600 mm gusset base plate. So the pressure under the gusset plate, pressure under gusset base equal to the load 3600 into 10 power 3 divided by the area of the base plate 700 by 600. So this is equal to W. So this W equal to is 8.57 MPa. So this is the upward pressure which is acting below the base plate. Upward pressure acting below the base plate. Now critical section is taken at XX. Critical section is taken at XX. So this is projection A. Critical section. At critical section at critical section A equal to, at the critical section A equal to, it is at the critical section projection A is equal to, total width of the base plate is 700 minus the column size 350, plus there are two cover plates 20 mm, plus there are two gusset plates of 16 mm, plus the thickness of the angle 15 mm, and there are two on both the side. So this divided by 2, this divided by 2, so that A equal to 124 millimeters. So the projection beyond the critical section equal to 124 millimeters. So the bending moment at this section, bending moment at xx equal to mx equal to, it is upward pressure 8.57 into 124 into 124 by 2. It is like a cantilever. So 124 into 124 by 2. So this is equal to, it is a 65886 Newton mm. Equating mx and moment of resistance. Equating mx and moment of resistance, we have that mx equal to 65886 is equal to 1.2 into Fy divided by gamma mo into Ze. So where Ze is the elastic section modulus of the plate. Ze equal to, it is 1 into t square divided by 6. 1 into t square divided by 6. Hence 65886 equal to 1.2 into 250 divided by 1.1 into 1 into t square divided by 6, or t equal to, we'll get t equal to 38.02, 38.702 mm. Okay. So now this is the thickness of the gusset base at the critical section. So actually that is 38.072, it includes the thickness of the gusset angle also. Therefore thickness of base plate equal to, it is 38.072 minus 15. So it comes out to be 23.07 mm. Okay. Or we can take this almost we can take 25 millimeters, round off to the next higher number, this. Now the pressure distribution under the base plate is W equal to 8.57 MPa. So the vertical, the force P will be found by, so 2P equal to 8.57 into 700. 2P equal to 8.57 into 700. So the point load which will be acting at the junction of the gusset angle and the gusset plate can be, it is 8.57 into 350. So the bending moment at YY will be, bending moment at YY will be, at YY section will be, it is equal to MYY equal to 8.57 into 350, half the base plate, 350 into 350 by 2. Okay, so at this critical section, bending moment is W into 350 into, it's a point of CG will be 350 by 2. Okay, so 8.57 into 350 into 350 by 2 minus the moment produced by the point load P. So So that is 8.57 into 350. This is the value of P. So that into the lever arm for P from the point of the load to the center of the plate. So that is 350 by 2. 350 by 2 plus 20 into thickness of the gusset plate. Okay. So now this is equal to MYY equal to 106,482 Newton mm. So equating this moment at the section YY equal to the moment of resistance, equal to the moment of resistance. So MYY equal to the moment of resistance, that is 106,482 equal to, it is equal to 1.2 into Fy divided by gamma MO into Ze. So Ze is 1 into T square by 6. So T from this equation it will be 48.44 mm. So as central portion of the base plate, as central portion of base plate, central portion of the base plate has bending in two directions, therefore half the thickness, half the above thickness is considered for base plate, hence that is T equal to 48.4 divided by 2 equal to 24.2 mm, or it is less than 25 mm. Hence provide thickness of base plate equal to 25 millimeters. Okay. So now design of the connections. That is how many number of bolts are required to connect the gusset angle and the gusset plate. Okay. So assuming ends are machined for a complete bearing, then load to be transferred by fastenings equal to half the axial load, that is 3600 divided by 2, so it is equal to 1800 kilonewtons. So the total fastenings on both the sides of the column have to transfer the total load, that is 1800 kilonewton. Okay. So load on each face of the column equal to load on each face of column equal to half, 900 kilonewtons. Okay. Now using 24 mm diameter shop bolts. Okay. So the bolt value we have to find out. So the shearing strength of bolt. Shearing strength of the bolt is equal to FUB divided by root 3 into gamma MB into NN into A and B. So this is equal to 400 divided by root 3 into 1.25 into 0.78 pi by 4 into d square. So this comes out to be 65192 newtons or 65.192 kilonewton. Okay. Now the bearing strength of bolt. Bearing strength of the bolt equal to 2.5 kb into d into t into fub. Okay, divided by gamma mb. So this is equal to 2.5. kb is taken as a 0.5. 0.5. D is the 24 mm diameter bolts. T is the thickness of the gusset plate 16 mm into FUB 410. FU it is, that is the ultimate stress in the steel, 410 divided by 1.25. So it is 157.44 kilonewton. So the bolt value equal to 65.192 kilonewton. So the number of bolts required will be number of the bolts required equal to 900 kilonewton. That load is to be transferred by fastenings on one side divided by 65.192. 65.192. So the number of bolts equal to 13.8. 13.8. So provide 14 bolts. Provide 16 bolts. 16 number of bolts. 16 number of bolts for connecting column to the gusset plate. Gusset plate. Okay. So here in this we have to provide 16 bolts. So in one line 8 number of bolts. Right. So total 16 number of bolts are required to connect a column to the gusset plate. Okay. So here same number of bolts also required to connect to the gusset angle of the gusset plate. So here there will be another 2 bolts like this. Right. So these are also 16 number of bolts. 16 number of bolts. So now 16 number of bolts are required. 16 number of bolts are required to connect the gusset plate with the column, and also the same number of bolts are required to connect the gusset angle with the gusset plate. Okay. So the side view, we can see here the number of the bolts are required to connect the entire assembly. Okay. So this is the design procedure. So in the design procedure we will be finding what is the first that the area of the base plate required. So area of the base plate required equal to the column load divided by the bearing strength of the concrete. Okay. So from that we have to find out what is the width of the base plate. So width of the base plate is kept in such a way that it will just project beyond the gusset angle. So once the one side is fixed, another side that is the length of the base plate is obtained by area divided by the width. Okay. So we will fix up what is the size of the base plate. Then thickness of the base plate is obtained from the bending moment criteria, that is at the critical section XX and at the section YY. We have to find out what is the bending moment, and that we have to equate with the moment of resistance of the base plate. So from the two conditions, that is at the critical section XX and YY, we have to find what is the thickness of the base plate. So from the two conditions we have to provide what is the maximum value. So that will be the thickness of the base plate required to resist the bending moment. Okay. Then design of the connections. So design of the connections are assuming that the ends of the column are machined. It means that half the load will be transferred by bearing and another half will be transferred by the fastenings. Okay. So on each side of the column face, the load acting will be 900 kilonewton. Then assuming 24 mm diameter the shop bolts, we have to find what is the bolt value. So shearing strength of the bolt in single shear and the bearing strength of the bolt. Okay. So from these two, the lesser value will be the bolt value. Okay. Next, number of the bolts required will be the load acting on one face of the column 900 kilonewton divided by the bolt value. Okay. So you will get 13.8 or that is we can provide 16 number of bolts. Okay. So 900 kilonewton divided by the bolt value 65.192. So it comes out to be 13.8. So we can provide the round number. 16 number of bolts are required to connect the column with the gusset plate.